Ready, sir?
Yes, I am ready.
Okay. Good evening to Jigar, sir, and one and all. My name is Ankit Patel, Head of Department of Aeronautical Engineering at Parul University. Today we have organized webinar on Introduction to Hypersonic Flight. During the session, if anyone having queries, then please ask me via WhatsApp on my number. Please note down my number: 9978225359. I repeat again, during the session, if anyone having queries, then please ask me via WhatsApp on my number. Please note down my number: 9978225359. 9978225359. As an expert, today we have Dr. Jigar Sura from Amity University with us. I would like to request Jigar sir, please proceed for the webinar.
Thank you, Ankit sir. So, students, today, as sir has said, we will talk about some fundamentals of hypersonic flow. So, there are not big equations or big simulation that I will be talking about. I will give you, in general, some idea about hypersonic flow. So, uh, to begin with, a very basic chapter of aerodynamics by Anderson, Mach number regimes. So those who are from aerospace or aeronautical background, they already know what are the regimes. So first or primary is subsonic flow. M is less than 1 everywhere. It is like almost all passenger jets, cargo jets that we see on our apps. They are from subsonic flow. They fly in subsonic flow. Then comes a region called transonic flow, which is mix of supersonic as well as subsonic flow. That is where Mach number is less than or more than 1. So that is known as transonic flow, and some passenger jets they do fly in this region. Thumb rule says we have zero point 0.8 to 1.2 Mach is transonic flow. So if you read any literature about Airbus or Boeing recent planes, they fly in the range of 0.85 and above. So they fly in transonic region. Then comes supersonic flow, like Sukhoi 30, MiG 29, MiG 21, Rafale, SR-71, all these planes they fly at more than Mach number 1. So we call that flow is supersonic flow. So what is hypersonic? Because if you look at Mach number distribution, then all three regime are over, less than 1, more than 1, and in the near zone of 1. So hypersonic flow is the subset of supersonic flow, or we can say that it is very high supersonic speed. It is like hypertension. We already have tension in our bloodstream, but if it goes beyond certain value, we call it hypertension. Similarly, we talk about hyperglycemia. So a hypersonic flow in general, we talk about Mach number 5 and above. But remember, if you ask anyone that hypersonic flow is above Mach 3, if he says so, we have to accept because it depends on the properties of the gas. So this figure, this image that you see is of X-43 hypersonic experimental vehicle by NASA, which is retired. Actually, it is the first plane without crew on board, which was able to fly using scramjet engine, which is useful for hypersonic flights in 2004. So this is the mothership or the launch aircraft for that plane, B-52B. It is also a retired plane. So hypersonic flow, when you want hypersonic flight, you cannot start with hypersonic flight required engine like scramjet or ramjet engine from the ground. You need somebody to take you up there and then you launch. So aviation is one of the mode of transportation, and it is the fastest transportation, technologically advanced transportation mode, I can say, because we started in 1903 when Wright brothers had taken flight at sea level at the speed of about 56-57 kilometer per hour, the speed at which right now we drive our bikes. And by 1969 we launch Apollo module and we reach moon, came back, and when it came back and when it was flying in the space, the speed was about 40,000 kilometer per hour. So within 63 years, we have achieved so many things in terms of speed. Now, hypersonics, when we talk about, it is associated with very high speed flight. So it is not a new thing. It has started since 50s when we started talking about high speed rockets which were able to launch the satellites and Apollo missions, lunar missions, and space shuttle after that. So whenever any object enters the Earth's atmosphere from the outer space, it reaches hypersonic speed within some seconds. Remember this. So as I said, if you talk about air only, we can say Mach number 5 and above is hypersonic flow. But what if we are on Venus, we are on Mercury, or we are on Jupiter, where the gas composition is different? So the characteristic hypersonic flow is like this. You have thin shock layer. If you observe theta beta m diagram from gas dynamics book or propulsion books, you will see that if you increase the Mach number, for the given value of theta, your beta value reduces. That means the distance between the shock wave and the object will reduce. So this becomes very thin. It is like you will not be able to distinguish between shock layer and your actual object. Similarly, on the opposite end, what happens is boundary layer becomes thicker. If you increase the velocity, if you increase the Reynolds number, the boundary layer tends to thicker. I can tell you that on space shuttle, there used to be thickness of boundary layer about 1 meter. That was to be the thickness when it used to re-enter from outer space. Then viscosity or viscous interaction. This is the thing which usually ignore when we do experiments in subsonic flight in our wind tunnels at ground or supersonic wind tunnels on our academic labs. But when you talk about very high speed, you cannot ignore the viscous effects. It is like you are rubbing the hand, rubbing your hand in winter. If it is 10 degrees Celsius, your requirement is different. If it is 0 degrees Celsius, rubbing the hand is different requirement. At that time, you cannot ignore the friction between the hands. Then high temperatures. Shock always increases the static temperature. So when you have very high Mach number, your shock strength increases. It makes the flow temperature very high. And that high temperature causes phenomena like vibration of the molecules. So till now, when we talk about supersonic flow, we talk about macroscopic thermodynamics. That is like taking statistical average value everywhere. But when you go into hypersonic regime, at after certain altitude like 50 kilometer and above, you cannot use macroscopic view only. You have to incorporate microscopic thermodynamics view. And this friction, this viscous interaction and high temperature causes large aerodynamic heating. So even though you are flying at 200 Kelvin temperature, 215 Kelvin temperature outside, just because of your speed, the temperature on the surface can become so high that it can melt the surface. And this is one of the reason where this Columbia fell. It met with an incident. So let's talk about in terms of number. For example, I am flying at 50 kilometers altitude, where from the book I have taken the temperature is 282 Kelvin and pressure is 87 Pascal. So on ground we have more than 1 lakh Pascal temperature. So you can think that it is almost vacuum or almost zero pressure value, where density is almost zero, like 1 gram per meter cube. If I am flying at Mach 8 and Mach 16, what will be the stagnation condition? Ideally. So stagnation temperature, if you use isentropic relations, you will get 3900 for Mach 8, but more than 14,000 for Mach 16. Similarly, stagnation pressure in terms of atmosphere, Mach 8 is only 8.4, but Mach 16 is 891. It is like 100 times more. Stagnation enthalpy associated with the temperature is 3.9 megajoule per kg. So if you use this only for 1 second, you have 3.9 megawatt of energy. And for Mach 16, it is 14.7. Or speed, if we'd like to talk about speeds, then speed will be 2.6 and 5.3 kilometer per second. So just by the time you think about going from Ahmedabad to Baroda, it will take only 1 minute maximum when you are flying at Mach 8. That is why you read the news that London to Tokyo or London to New York within 2 hours of flight, दिल्ली में ब्रेकफास्ट करके, लंदन में लंच करके, न्यूयॉर्क में डिनर करेंगे. All these things are possible only when you fly at hypersonic speed. Let's say we want to slow down the flow. What happens? Just using the normal shock. So M2 will be 0.39 and 0.38 for Mach 8 and Mach 6. So almost similar range. But temperature is 3700 to 14,000 Kelvin. Similarly, pressure is in the range of 6,000 Pascal to 26,000 Pascal. And the speed, which will reduce to 400 meter per second to 900 meter per second. Still high, but it is quite less as compared to the original speed. So if we say 14,000 Kelvin temperature or 3,700 Kelvin temperature, there is no metal which can survive this much of temperature continuously. So at that time, the Almighty God, the Almighty nature comes with us for help. What happens? When you increase the temperature, the gas does not remain perfect. Our air does not remain perfect air. What happens once you cross 2000 Kelvin temperature? O2 becomes 2O. That means you need oxygen. Remember, you need oxygen molecule to burn the fuel. You don't need oxygen ions or oxygen as an individual atom. So 2000 Kelvin to 4000 Kelvin, O2 will become 2O. So now already your 20% of air is gone in terms of property, we can say. After you cross 4000 Kelvin, your N2 will become 2N till 9000 Kelvin. So once you reach 9000 Kelvin temperature, you don't have oxygen molecule or nitrogen molecules. What you will have is only oxygen atoms, nitrogen atoms. So our air is gone. You cannot use gamma is equal to 1.4, Cp is equal to 1 kilojoule per kg Kelvin or similar equations now. You have to use macroscopic approach. How much percentage of O is available, how much percentage of O2 is available, how much percentage of N or N2 is available. Still, if you talk about space shuttle re-entry, the temperature can rise above 9000 Kelvin, then it becomes oxygen ions and nitrogen ions. If you think that nitrogen ion and oxygen ion means electron is now free to combine with some other molecule which receives the electron. Everything has now free electrons, and flow of electron is the current. And when you have the current, you have electromagnetic field or electromagnetic force. So just because of this rise in temperature, you will have one more additional force, which is electromagnetic force in and around the any space shuttle or any vehicle which is flying at hypersonic speed. Now this is the reason which has led to the communication blackout. It used to happen every re-entry by space shuttle. Because of this presence of free electrons in the shock layer, there used to be communication blackout. At that time, the astronauts have to calculate all the details with pen and pencil on paper. So this used to happen. This was normal because you need radio waves to transmit your location and everything on the ground. If it does not happen because of this issue, you can't do anything about it. So that used to be like about, if I am correct, it is about 3 minutes of blackout where you don't know where the space shuttle is and what is happening inside it. So we are talking about such a large speed. What comes with this is challenge. Experimentally analyzing the flow field for hypersonic flights. So what happens? What is required is Mach number, similarity rules, or pi theorems, Buckingham's pi theorem that we have studied. So Mach number, similar Mach number you have to produce. Reynolds number, similar Reynolds number you have to produce because both of them are non-dimensional. Plus you have to take care of temperature. Now temperature is the difficult thing to achieve and control. The reason is temperature means weakening the structure. If you say I want to store something, some air or some gas or some liquid, some fluid at 100 bar pressure at room temperature, it is possible. You just keep on thickening the wall, you design the joints properly, you will be able to store it. But if you say I want to store something at 200 degrees Celsius even in at 1 atmospheric pressure, then also it is difficult because heat transfer will keep on happening and it will reduce the temperature eventually. So these three things are experimental challenge for hypersonic flow. So other some of the labs can match Mach number. Some labs they match Reynolds number. Some labs they match temperature ranges. So different facilities have different capability, and when you take all the data from this different kind of labs, you have to patch them to get a final view of the final scenario for the flow field. So experimental data is the patchwork of different data taken in different facilities under different conditions. It is like somebody will do it Mark 2, somebody will do it Mark 5, somebody will do it Mark 10, Reynolds number will be variable, and all these things you have to bring to one place and use data analytics systems. So if we don't do experiment, we can go with theory like Laplace equation, Maxwell equations, Planck's constant, a normal equation that you can solve directly. So what happens? These equations, once you cross in fact supersonic boundary, that means when you are in supersonic region, usually your flow is non-linear. So non-linear structure of the equations will not allow you to find out the answer easily. Second, the same thing, you cannot incorporate the high temperature chemically reacting flows. The things that I said, oxygen is becoming oxygen atoms. So how can you incorporate that? Because it is a natural phenomena. Once you put there, it has to go through statistic, how much percentage of oxygen is there, and how much at what rate oxygen molecule will become oxygen atom will become oxygen ion. All these things, it has got no fixed boundary. Remember this. You cannot say that just because 4000 Kelvin is the temperature, once you reach 4001, all oxygen will become oxygen atoms. Not possible. All these things will be taken over by computational fluid dynamics, or CFD, as you know, using ANSYS, Hypermesh, Nastran, Patran, OpenFOAM. There are n number of softwares, n number of codes written for subsonic, supersonic, transonic, hypersonic flow through CFD. So in hypersonic field, usually people do computational fluid dynamics analysis first, and they verify that with experiments, because experiments are costly here. So as I told you that there is effect of high temperature, which is quite important. It is something like this. At high temperature, your thermodynamic property change. You know Cp is a function of temperature. In some equation you would have used, or if you use gas turbine theory, there you see that in the compressor use different Cp value, and turbine use different Cp value, because combustion changes everything. Similarly, transport properties. Now transport properties are conductivity, viscosity, all these things. So when you change the temperature, viscosity changes. When you change the temperature, thermal conductivity changes. Now if they change, your Prandtl number change, your Nusselt number change, your Biot number is different. So this will lead you to difficult equations, or equations which are difficult to solve. Then high temperature, that means high heat transfer rate. So in supersonic flow, we don't, when we solve normal Laplace equations using supersonic inside the supersonic flow, we don't talk about heat transfer rates usually. In fact, when we talk about inviscid, we don't talk about it. But in actual case, for hypersonic, it is very high heat transfer rate, which can lead you to melting of the skin also. Variable ratio specific heats, gamma. So gamma for air, room temperature, you take 1.4. For the same gas, if you change the temperature, your gamma changes. In fact, once you cross certain boundary like 2000 or 3000 Kelvin temperature, your air does not remain air itself. It becomes a mixture of different atoms. At that time, gamma is totally different. Another thing, all analysis requires some type of numerical solution. As I said, pure theory needs non-linear equations which are difficult to solve analytically. So you need numerical methods. like Gauss elimination method or Taylor series equations or Picard's method. All these methods are required to solve hypersonic equations. In fact, Navier-Stokes equations, we are not able to solve even as of now. As on date, it is not possible to solve Navier-Stokes equation thoroughly. We have to assume so many things. Another important aspect is ionization. You know that solid, liquid, gas, and the fourth phase of the matter is plasma. So once you ionize the gas, it becomes partially ionized plasma. You have some amount of gas also, you have some amount of plasma inside the shock layer around the space shuttle or hypersonic plane. Now that plasma contains electrons. Electron means current. Current means electromagnetic field. And when you have electromagnetic field, your aerodynamics does not remain only aerodynamics. It becomes part of magneto-hydrodynamics. It includes Maxwell equations, that current flows and the force acts on the normal direction to the current, and all these things happen. So a simple equations of aerodynamics, you have to include magneto-hydrodynamics equations. So you just think that how difficult is it to include all the actual scenario for hypersonic flights. Non-adiabatic effects of the radiation. When we have very high temperature, radiation becomes a dominant aspect. In fact, for hypersonic flight, sometimes it can reach up to 30% of the total heat transfer. So we say that air has convection, air is the gas. In the gas, it happens convection. Radiation is very low on the ground, but at very high temperature, that radiation has to be controlled, and it changes the entire flow field. So let's talk about some classification, which is just for the information. Why do we need hypersonic equations differently from supersonic equations? So there are different classifications based on the temperature range and certain properties. We have calorically or calorifically perfect gas, which has constant specific heats, like air. You take gamma 1.4, Cp 1.005 or something like that, and you maintain that continuously. So that is calorically perfect gas. When you are dealing with this gas, your life is easy, no problem. Then life becomes little difficult when you go into thermally perfect gas regime, where you have variable specific heats. But this very specific heat are function of only temperature, nothing else. So still pressure is out of the question. And up to 2500 Kelvin, you can talk about thermally perfect gas. So the benefit of this thermally perfect gas assumption is, when you are on ground and you use ground based facilities, you don't reach more than 2500 3000 Kelvin temperature in experimental facilities for hypersonic flow. So we can assume thermally perfect gas and survive with that. But if you really reach hypersonic flight Mach 8 above, Mach 16 above, Mach 26, 36 and so range, you will have the chemically reacting mixture of perfect gases. That means nitrogen is reacting with oxygen, carbon dioxide is reacting with oxygen, or because of the temperature, carbon dioxide becomes carbon monoxide plus oxygen, ozone changes its property, all these things. So multi-species and chemically reacting gas. Now what is the implication of this assumption? Usually when we solve any problem using CFD or numerical methods, you use mass, momentum and energy conservation equation. All these three equations are sufficient to give you the answer. But when you include this property, chemical reactions, you have to include one more equation, which is known as conservation of species. So in the given control volume, if you have 20% oxygen coming in, so same 20% of oxygen should go out in any other way, not necessarily as an oxygen molecule. It can be in terms of CO2, in terms of H2O, in terms of NO2, N2, or any other nitrates. In this also we have two different things. One is non-equilibrium, which is function of pressure, temperature and time. Now, should we use this or not? It is a question, big question, in fact. Just think that you are in the big room. Just giving you a weird example. Or there is a big room in which you are not there. It is empty, and some firecracker bursts inside it. If you take a reading of temperature or pressure or some other property which you can measure like sound at every 1 microsecond, so you will see the fluctuations initially, right? You will see the fluctuations of pressure and temperature initially. So that is like non-equilibrium we are talking about, because with time in terms of microseconds or milliseconds, we are seeing the change. But if you take on reading even after the firecracker is burst, after 2 seconds, 3 seconds, then entire room will be at some same temperature and pressure conditions. So that time you can say that my room is under equilibrium. So function of pressure and temperature only. So whether we should use non-equilibrium or not, it is all the question is. This question arises because if you say my N2 is becoming 2N or O2 is becoming 2O, it is a process, natural process, or any natural process takes finite time. And during that finite time, the molecule is traveling at hypersonic speed. So it will cover certain distance. So during that distance, you cannot say that whether it is N2 or whether it is 2N in that gap. So this creates a trouble when you talk about non-equilibrium problems. But if it is equilibrium, again your life is relatively easy but more difficult than thermally perfect gas. And this fourth thing is real gas. Usually in the book of Anderson, they have given one perfect explanation about real gas, is that effect of intermolecular forces. Now this happens when you are at very high pressure and very low temperature, which is not part of hypersonic flow. But this is mentioned because we talk about real gas effects. If you read some literature in hypersonics, they will talk about real gas effects or real gas conditions. There they talk about vibration of the molecules, energy contained in that molecules, all these things, which is actually part of chemically reacting mixture, but not a real gas from Anderson perspective. That is why I have mentioned. So when you talk about solving the hypersonic problem numerically, first you can start with constant specific hits. Life will be easy. Just try to solve that. You will get all the wrong answers. Then you change the specific hit as a function of temperature. You will get still better answer, but acceptable answer, I would say. And then if you have if you have courage to write down 10 or 11 equations and to solve together using any softwares, then you can go with chemically reacting mixture of perfect gas and your life will be miserable at BTech level. So one phenomenon that happens is shockwave boundary layer interaction. Now in 1967, when this was not known to anyone, this plane X-15, X-15 of US Air Force became the first victim. It was non-fatal, nobody died in that. But this is one of the phenomenon, one of the aspects of hypersonic flow, which needs proper attention at the time of design stage. So what happens, you have multiple pylons where you mount your weapons or you mount your fuel tanks, or you have some curvature like rudder section or lifting control surface and all these things. So because of that, there will be shock wave, which is known to us that supersonic flow causes the shock waves. Now that shock wave impinges on the boundary layer of some other surface. It impinges on the boundary layer of the some other surface. It is simple way we can say that बुलेट के पीछे जो साइलेंसर से जो आवाज आती है ना, उसके साथ में गरम गरम हवा भी आती है साइलेंसर से. It touches your leg when you are standing some little bit far away. You feel that thrust you feel from the bullet. Similarly, shock wave generated due to one surface It goes and impinges on the other surface where you have boundary layer. Now this causes local heat regions or local peak of heat transfer, and which can be severe. In fact, in this plane, it created a hole on the fuselage, and all high speed air rushed inside the fuselage, damaging all the equipment. Fortunately, the pilot could land the plane and he survived. After that, people started thinking about this problem. And let me tell you, this is the there are many researchers who are working only in this field, SWBLI, either experimentally or numerically. And also, based on my experience, I have seen that you can match pressure distribution in this region numerically with experimental, but it is not possible to match heat transfer data that you get from experiments with the heat transfer data that you obtain from numerical methods. So still there is a gap even after almost 50-60 years of research. In fact, when they started talking about ramjet engine and scramjet engine in 50s, people thought that it will be easier to design the engine and fly. They were thinking about 10 to 20 years of time frame. What they did not know was that high temperature flow, high speed flow will cause high temperature onto the skin surface, and it will not allow you to fly at that particular speed because of material restrictions. So local peaks of heat transfer in the interaction region that can be extremely severe, and this happens, that I can tell you. Now, experimental facilities for hypersonic flights. If you talk about subsonic planes like Cessna size of plane or Embraer type of business jet, then you can have full scale wind tunnel for subsonic flow, and there are there in the world, which can have the large room which can accommodate the entire plane. You can start the flow using gas turbine engine which drives the fan, and you can generate the flow. You can run those tunnels for minutes together or hours together. Even in your lab, when you run the wind tunnel, you run for about 20 minutes, 30 minutes together. Of course, it comes with the electricity bill, but still you can run if you have money. If you talk about supersonic wind tunnels, we need blow down systems. That means we have to store the energy in terms of compressed air first, and then we expand the flow, and you will get supersonic flow. There also you can run tunnels in a time of minutes. You can say that we cannot go hours together, but 1 minute or 5 minutes, 10 minutes, sort of, you can run the hypersonic supersonic wind tunnels. But when you talk about hypersonic wind tunnel, let me tell you, if you achieve 1 minute of test time, 1 minute, 60 seconds, then also it is a great achievement. It does not come free. It comes with a lot of cost that I will tell you later. What are the complicated issues? Second facilities around the world is shock tunnel. Hypersonic wind tunnel is not a different than supersonic wind tunnel. Only the design is different. That's all. So supersonic wind tunnel, if you modify, you can convert it into hypersonic wind tunnel. No problem with that. But shock tunnel is totally different thing where you can get test time of milliseconds. I can repeat, milliseconds. And when I say milliseconds, I am not talking about more than 5 milliseconds. When I was doing experiments, I used to get only 1 milliseconds of test time. So in that 1 millisecond of test time, you have to complete all the data collection through high-speed sensors. So what are the requirements if you want to design hypersonic test facilities for your nation? Then what are the requirements? Or any wind tunnel, if you see, more or less similar requirements are needed. That is, you should be able to test a model of sufficient dimension or scale. Like, you cannot say that my wind tunnel or my hypersonic shock tunnel can test 1 mm of 1 mm long model. 1 mm is nothing, or 10 mm is also nothing. So sufficient scaling is needed so that you can put your sensors. All the sensors in real life comes with finite size. So you should be able to mount it properly. Plus there should be distance between two sensors so that the structure is not weakened. You have to think about how will you bring out the cables from the sensors without affecting the flow field. All these things you have to think. Similarly, you should have sufficient run times. Now, what is this? Let's say you are able to generate 1 kilometer per second of flow somehow. Okay, that means 1000 meters per second you are able to get. If you say I want to test it for 1 millisecond, only 1 millisecond, that means you need your flow will travel 1 meter length. Now, if your model is longer than 1 meter, in that case, then it will not be able to give you the data properly, adequate way, I can say. So, run times means the amount of distance your flow can travel divided by the maximum or the longest dimension, or in the direction of the flow, whatever is your dimension, that value. Like you have 1 meter of distance covered 1 millisecond, then you can have roughly about 1 by 3 meter, that means 300 mm, 350 mm of model size, so that you can have 3 body passes, means 3 times if you multiply the dimension, you will get that much of distance covered. So this is most important, otherwise you will not able to get any data. You cannot say that I'm just like you are searching inside the room something in the night, just switch on the lamp and switch off it again. No, you should provide some amount of time to search. It is like this. Then dynamic pressure. So dynamic pressure is responsible to give you the data for CL, CD, coefficient of lift and coefficient of drag. So if you have very low dynamic pressure, it means no lift is generated, almost. And remember, any material comes with the weight. So the pressure should be sufficient enough to lift the model or change the orientation of the model or create some force. Then only your sensors will respond. So sufficient amount of dynamic pressure needed. And quality of the free stream. This is important aspects, and can you keep on increasing the velocity. So if you say academic scale, subsonic, low speed wind tunnel, you have noise coming, vibration coming, all these things we can handle, no problem. But when you go into compressible subsonic flow, like testing of Boeing and Airbus jets, then you have to have a proper quality of the free stream. When you reach in the hypersonic field, also you need quality free stream, because Reynolds number, the thing that you read that 5 into 10 to the power 5 and 2 into 10 to the power 5 will cause from laminar to turbulent and all these things, it has one condition, star conditions apply, is that the noise inside the flow affects the Reynolds number transition. So if you have quiet flow, very quiet, then even after crossing 5 into 10 to the power 5 Reynolds number, you will have laminar flow. So remember this, a good quality of free stream is required for anything, for any wind tunnel testing or shock tunnel testing. Now, what are the ways you can test? After you achieve all these conditions, all these requirements you satisfy, what are the ways you can test the hypersonic flights or hypersonic planes? One is you duplicate everything. Duplicating means matching of all the aspects of flight environment, which you are not able to achieve usually. It is very difficult to achieve all these things. First, you don't know the weather condition. You say that air pressure and temperature at some altitude is this much from the table ISA, fine. But on that day, it will be different. ISA is for standardization, but every day it can change actual cases. So we have to calibrate it. Even when you fly from Mumbai airport or when you fly from Delhi airport, that or inclination or the height of above sea level is not much of a difference. Still you have to take readings for that. So duplication for hypersonic flights is not usually achieved. Replication. Replica means similar way but different material. It's possible. Like if you want to make Taj Mahal from wood, you can make it. It's a replica. So temperature, pressure, velocity, chemical composition is matched with the flight medium. So what is the benefit here? you need not to use air only. You can use carbon dioxide, you can use argon gas, you can use helium gas and get the reading. This is also known to you by Buckingham pi theorem that you can change. If you are talking about non-dimensional parameters, it should match the Reynolds number and Mach number. But it is also difficult because air you can take just by using the compressor pump, but if you take argon or if you take carbon dioxide, you have to evacuate the entire air from the system, then you fill that, then you run it again, you keep on checking for quality of the flow, all these things. So final benefit thing that you can do at academic scale or low, if you don't have budget, is simulation, which is nothing but reproduction of only important parameter, which are usually non-dimensional. That means you match Mach number. If you go to IIT Bombay, if you go to IIT Madras, or if you go to DRDL Hyderabad, they have the hypersonic shock tunnels. So there, it is not possible to put entire full-size plane or half-size the plane inside the test section. Not possible. So they simulate. What do they simulate? They say that, okay, I am simulating the flow of Mach 8 or Mach 6 or Mach 10 based on the dimension of the nozzle and conditions of the wind tunnels, shock tunnels. So they reproduce the same parameter like Mach number. They take the reading, you non-dimensionalize it and put it. If some correlations are required, you use that, and then you supply it to other agencies like BrahMos Corporation. So duplication, replication, and simulation. So as I said, duplication problems are non-uniform phase stream over a wide range of conditions. You don't know. You say you want to simulate the flight from starting from takeoff to reaching cruise altitude of 50 kilometer in the wind tunnel. Not possible. You cannot control everything there. Lack of equilibrium due to short or small test time. As I said, in hypersonic wind tunnels, if you achieve 1 minute, it is a great achievement. In shock tunnel, 1 millisecond to 5 milliseconds. If somebody says I am getting 10 milliseconds, you have to use their tunnel extensively. Now this is the thing which again not in our control, comes from the nature. It is contamination of the flow because of erosion. The supersonic flow, you need CD nozzle, convergent divergent nozzle, and you know also, or you understand that with high velocity comes high friction. So that high friction can eventually rub the metal surfaces. Okay, rub the metal surfaces of the nozzle. That means the area, cross sectional area of the nozzle changes, and small particles, very small, micron size or maybe nanometer size, that metal particles which are flying with the air, which it will change the property of the flow finally. If it hits one sensor, it will give you the more reading every time, not necessarily that it is the same case. And acoustics and enthalpy fluctuations. You generate the flow, anything that moves have the noise. Remember this. You move the bicycle, the fan moves, the compressor moves, you move, anything that moves has an acoustic signature. So this causes the change in the property of the flow field. It is possible. In fact, you can search on YouTube, people are using this acoustics for flame out, or I can say the extinguish the flame using acoustic, only noise, only sound, high low frequency noise. And enthalpy fluctuation. So every time or during the entire experiments, you don't have same enthalpy values. It's not possible by nature itself. Even you take small wind tunnel in your lab, you will not get same velocity continuously. You will get fluctuations, maybe negligible, but fluctuations. So it is not, it is the problem. Another is surface roughness and scaling effects. Material that you use to make the model, material that you use to design the tunnels will have roughness issue. Honing that you have to do when you talk about gun, rifling, all these things required. So this surface roughness changes the flow property. It can make laminar flow into turbulent flow, remember. And scaling effect. If you say that there is a wire or there is an antenna on the from the nose of the plane, Airbus normal subsonic plane I'm talking about, to that rudder section of the plane, which is having a diameter of 10 mm. Let us say it's 10 mm is large size, but let's say it is there. If you want to scale down 1 by 10, it will become 1 mm. Now 1 mm wire will have different effect than 10 mm wire. So scaling will be a problem. So let's see what are the different shock tunnels or wind tunnels around the world. Not many, I have not taken many photographs. But these are coming from the websites only, just to give you the idea what is the size of the experimental facilities. So this is T4 free piston shock tunnel, which is there in University of Queensland. It is one of the leading institute doing research in hypersonic flow. Let me tell you. So if you see the dimension, the length of the compression tube is 26 meter. The length of the shock tube section is 10 meter. And nozzle can generate 4, 6, 7, 8 and 10. It is not generated by a single nozzle. Remember, you have to change the nozzle. And changing the nozzle will take more than 1 week time sometimes, because you have to align everything again. Nozzle supply enthalpy range is 2.5 to 15 megajoule per kg, and supply pressure range is up to 90 megapascals. The piston that drives into the compression that goes into the compression tube is 92 kg. So think that 92 kg is almost equal to weight of the Activa 110, near to 100, 110 curve weight of Activa or scooty range. So that much mass will be traveling at least 60 km per hour speed. At least I'm saying. Think about the momentum achieved, and think that to achieve that momentum only with air, it is like you blow the air to drive the scooty at 60 km per hour speed. Think how much power you will need. Okay, so hypersonic test facilities need a lot of power. There was a thing that I have heard, I'm not sure, that DRDL Hyderabad wanted to design electrically heated shock tunnel. So they calculated the power, it was going into megawatts. It was like that. Let me show you the video when you run this wind shock tunnel, what kind of things that you see inside the test section only. It is a small video. Let me play it again. It was not playing. Yeah. Yeah, see the flow is coming and going. The white line is the shock region. And it's over. It says 11 seconds of recording. But remember, 11 seconds is the recording after taking the data. Actually, you will not get more than 1 to 2 milliseconds. So you take multiple frames per second, more than 1000 frames, and then you compile them. Another shock tunnel, which is again piston driven, is it Caltech. It is old wind tunnel actually, shock tunnel. It is also same way as University of Queensland. In fact, NASA has collaborated with University of Queensland for this research, and Caltech is one of the best university for aerospace engineering that you know. So it also has the piston you can see on the right side of the screen. That piston moves and it compresses the air, and the primary diaphragm is of 7 mm thickness of steel. So think that a metal plate of 7 mm thickness is burst. It is exploded. It is not punctured. It is exploded to generate the shock wave, and you will get hypersonic flow for 1 or 2 or 5 milliseconds stop. What is the specification for this? Maximum diaphragm 130 megapascal, maximum reservoir 15 megapascal, compression tube length 30 meter, shock tube length is 12 meter. Piston mass again Activa mass 120 kg, near to Activa mass. Do we have it in India? Yes, recently commissioned about 2-3 years back at Trivandrum VSSC ISRO. 1 meter hypersonic wind tunnel. What is that 1 meter? Is a test section dimension. The blue, if you see blue pipings, behind that you will see one small gray color structure, brown color structure. It is a test section. The two small cylinder type of things that you see on towards the middle left region is the nozzle. So different nozzle, different Mach numbers. These two vertical structure, if I am correct, they are the heat exchanger to heat up the air only. And this was commissioned in 2000, if I am correct, 2017, 2018. Recently it was commissioned and it is working fine. It is the third largest in the world. Please remember. Capability to simulate 6, 8, 10 and 12 Mach number. Nozzle exit diameter, as I said, 1 meter. Reynolds number range is 1 to 80 million per meter. Storage system is 300 bar and vacuum system is 10 to the power minus 2 millibar. So you can take the ratio of pressure 300 bar divided by 10 to the power minus 5 bar. That much of the pressure ratio. And just find out the Mach number if you want to calculate. And that storage heater system has 1550 Kelvin temperature. So air will be bring up to 1550 Kelvin temperature and then expanded to generate either Mach 6 to Mach 12 flow. There is another facility available at ISRO, which is shock tunnel, which can test up to 4.5 kilometer per second flow, and Reynolds number can go up to 3.3 million. If you want to, let me show you not the video of this wind tunnel or shock tunnel, but another shock tunnel. How fast the experiment happens, just for that. That's all. Over. That explosion that you heard is the experiments. That's all. And just see the recoil action. Just play again. So that is the sound of explosion of the primary diaphragm, which is metal of thickness of maybe 5 to 10 mm also, depends on the design of your system. So that 1 millisecond is crucial for you. So if you want to explore hypersonics, and if as I said it is difficult, what are the things that you can do in future as a MTech, PhD or as a researcher? You can upgrade the experimental facilities. It is always there. Upgradation scope is always there. Reduce the expenditure. Second, numerical solution algorithms. If you are interested in mathematics, you can develop the algorithms to find out the solution of hypersonic equations. Then stability and control, which we have not talked about. Not what is usually people don't talk about it because we have not made any flight till now, successful flight with crew on board. Remember, either you have scramjet engine flying alone or you have people flying with rocket engine. And only two things are available. Another option is BrahMos. So BrahMos 2 is Indian hypersonic missile, which is in collaboration with Russia, as you know. BrahMos is the only supersonic cruise missile. They are developing hypersonic missile, and for that IISc Bangalore is the center of excellence. Another important thing is passenger comfort analysis. Why do I say that? Till now people talk about only unmanned missions, but when you put passenger on board, you have to talk about their comfort. How fast you can accelerate the plane, how fast you can decelerate the plane, at what altitude how much oxygen do you need. All these things comes in picture once you have passenger on board. And so many other aspects, anything that you think about for hypersonic, you can work on it, because as Van Dreist is one of the well-known scientists in field of aerospace, the two major problems encountered today in aeronautics are determination of skin friction and screen temperature of high-speed aircraft. You find out the way to measure this or to determine this numerically, you will get maybe Nobel Prize. Remember this. These two things are very difficult to calculate, measure, any method possible. People are still struggling. You will not find much of a data. So that's all from my side. If you have any questions, I guess we are about to complete as per the time. I hope you are able to hear me properly, and thank you very much. Uh,
Hello. 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 Uh, Hello everyone. If anyone having queries, please ask me via WhatsApp number. My WhatsApp number is 9978 225359. I repeat again. My WhatsApp number is 9978 225359. If anyone having queries, please ask me via WhatsApp number. My WhatsApp number is 9978. Okay. There is no question from audience, sir. Thank you, Jigar sir, for sharing. Hello. Hello.
Hello, Ankit sir.
हाँ हाँ सर.
Okay, I'm back. I hope people. When did it
One
stop?
minute, sir.
Okay, fine.
Just a minute, sir. 1 minute.
Okay,
Someone asked the question.
okay, fine.
Sir, one student asked the question: which two things have said by the sir,
Huh?
which is difficult to
Hmm.
find? Which two things which you
Oh,
have
that
said
was
to be difficult to find?
yeah, yeah. One is skin friction. Another one is skin temperature. That means viscous forces, viscous drag,
Okay.
skin friction,
Another,
and skin temperature.
which one is a good book to study the to
You
study the hypersonics?
We can start with Anderson by Hypersonics by Anderson. It is a good book. Other book, if you want like historical perspective and experiments carried out by different agencies, then there is a book from Puran and Murthy, Curran and Murthy, AIAA series. There is it is there. That is also useful. But to begin with, we can read a chapter in aerodynamics by Anderson. There is a chapter on hypersonic flow, and hypersonic and high temperature gas dynamics is the book by Anderson for only hypersonic flow entirely written by him.
Uh, Please repeat two things which you have
Huh?
said.
Huh?
Which two things have said by the sir which difficult to find? Another.
Yeah, one is skin temperature, another one is skin friction.
Any question from audience? Please.
I guess no, there are no other. Okay, that's the
Any question from audience? Please. Thank you, Jigar sir, for sharing your precious time. It was very informative session with full of the knowledge. I hope students and faculty have
okay.
enjoyed it,
Thank you.
and we will meet with soon another such a good webinar. Thank you. Thank you, sir.